those of you who have been here before know what this is about. We take some of, or you're Canadians, a boot, some of the, actually the best cars we've seen in design this weekend are sitting here in front of us. So I'll just get rid of all the commotion right away and say these are the best two EV cars we saw in design and the two finest internal combustion cars we saw in design. We're going to go over some of the details on these, and we're going to have some of these students who designed and built and validated these cars give you a few more details. Hopefully they will give you enough to help your cars get even better, to get to this level and beyond, because it's a moving target. They keep getting better and better. Just for quick review, we've got here Michigan State, car 81, and we've got Auburn, car number 79, the internal combustion cars. And then we've got University of Washington, car 205. I should say Washington. I'm sorry, Washington. And then car 208, Wisconsin-Madison. So good job for all four of you to get here. It's quite the honor. What we like to do is, in design, we talked about this a lot before, it's really not about just how the car is built. That's one part of what we do with design, but it's really your whole approach towards your engineering process, how you communicate with each other, how you communicate with the former members of your team, and how you plan to communicate with future members of your team. It's more about how you're going to be a more well-rounded engineer and not just, can you build a great race car? Because if you're a good engineer and you can help manage a team, you'll build 20 really good race cars, not just one, or you have the capability of that. Remember, this competition isn't about just going racing. This is about becoming a great engineer. So hopefully you get some good inspiration from the students, and these two schmucks up here can tell you a few things too. Steve Fox is a longtime chief design judge and co-captain for the Michigan event too. So long time. He's been always fantastic in getting this event all going. I always want to give him a quick round of applause for his work.
And Dave Retz is the design captain for Formula SAE Lincoln. We could not do this without you, Dave. He pours in untold hundreds of hours of work ahead of this event, recruiting the design judges, getting the schedules done all by himself. He does this all by himself. At Michigan, it takes us 4 guys to do this amount of work. Dave does it by himself. Thank you very much, Dave.
What he's just proved is that I'm not a very good manager. I can't work with people, so, or I just do a lot less. Okay, first we'd like to start with car 205, Washington. We've got a few students up here we'd like to have come up. I think Peter, Ty, or Jonathan, perhaps. Come on up. You got the mic here? Okay.
The Washington car is a full monocoque frame, 10-inch wheeled car. It's got 2 rear motors on it. It's got a three-element fixed front wing, a 3-element rear wing, and a 2-element side wings on it. It's also got a sprung under tray, and there's various other different elements to this design that the design judges uncovered that it just shows real brilliance in design work. And we elected that instead of just running down the laundry list of stuff that's on the car, to rather let the 2 brilliant engineers that put this together talk about it themselves. So guys, take it away.
Yeah. Does this work? Cool.
What I'd like you to talk about just briefly is give us a rundown on the electric motor scheme on this car. What did you guys do for propulsion?
So we have 2 MREX 188 motors that just came out last year, one driving each rear wheel, and then a planetary gearbox on each rear motor for gear reduction to a half shaft to our hub on the rear tires.
And your energy storage?
You want to talk about?
Sure, yeah. So accumulator, this year we opted for more energy capacity than previous years because with the redesign of our chassis and our air package, we're losing a lot more energy to drag. So we went from a 4S 63P, or opposite, 4P 63S pack to a 4P 70S pack. That means you gain a lot of energy, but also a lot of mass in your batteries. So the whole design of the accumulator this year was pretty much centered around trying to drop mass wherever we could. So we actually went through the process to validate a composite accumulator through the SES process, and spent a lot of time working on the specific cell stack up, removing material wherever we could, and really just pulling the package down as tight as we possibly could.
The mic like that.
Yeah. Okay.
The mic works better when you talk into it. So we didn't rehearse this ahead of time, and I might be asking you a loaded question, but did you finish endurance?
We did. We did.
Awesome.
We,
Okay.
we're maybe not driving as fast as we could have been, but we did
How many wheels
finish.
are being propelled?
That's the second question. How
One
many?
wheel was being propelled.
Okay, and you were propulsing the car with one
We were,
right rear
we were.
tire, correct?
Yeah. Unfortunately,
you want to
after
explain what happened on that?
yeah. So after we went through E-Tech, we had 2 functional motors. Sometime between E-Tech and brakes test, we lost one of the inverters. We think it probably happened during rain test. We're not totally sure the cause. We broke down the inverter last night and just couldn't fix it in time. So Peter drove valiantly with one wheel, and we finished. Would have been nice to go a little faster, but we did make it through.
It's a classic example of persevering in the face of adversity. You don't give up. You never give up. You keep digging until you just get to the end. Now, the thing that I find interesting about this particular car, you run 2 rear motors. You do not run a differential, so you're doing torque vectoring, right? You want to talk a little bit about that?
Yes.
When you do have 2 rear motors?
Yeah. Well, when we do have 2 rear motors, we have active torque vectoring and traction control based on how the car is currently performing. It was actually, I think, the vehicle dynamics side of this. Peter is more equipped to talk about. We actually have a separate controller in the car from the electronics perspective that is doing all of the logic control for the torque vectoring system, and we're getting feedback through the motors and inverters the whole time.
Yeah, I'm not going to talk too much about it. Basically, we just use like vehicle speed and the IMU data to like logic out the torque request on both rear wheels.
So you're not going to give away any secrets here, or what?
I'm going to try not to.
All right, so what drives the torque vectoring? Lateral acceleration? Steering angle? What?
So in years past, we've actually kind of had like a faux torque vectoring system where it was just based on vehicle speed and steering angle, meaning like a selected yaw rate of the car. We found that was like way more difficult to tune, and it wasn't as driver friendly. So we started like basing it off of like more like IMU data lateral acceleration to like have a more calculated and tunable system.
He's being pretty secretive. You want me to start putting the bamboo shoots under his fingernails for you?
I don't suppose the model you developed, the lap time simulation model you've been working on for a number of years, included a one-wheel drive. Okay.
We could have, but we didn't.
But I'd like to ask you about a couple things. One is when you did the torque vectoring setup, did you try with and without the lap time simulation as part of that, or lap time simulation with and without the torque vectoring? And how did it change when you did try that, if you did?
Yeah. So is this working? Okay. Cool. The simulation like equipment we use is not just a lap time simulation. It's actually what we call like a competition simulation. So it's not just incorporating like how fast the car is going to be on a given endurance or autocross course. It's also like a simulation of how we're gonna score in skid pad, how we're gonna score in acceleration, and how we're going to score in static events as well. But to touch on the like torque vectoring. It was really finicky. I'm not super great at MATLAB, and for me to develop into that was really difficult. My like focus this year was actually to optimize the aero system for our energy consumption so that we could drive at full speed during the endurance. And the torque vectoring like system was difficult to like how would you say like have a continuously changing torque request per wheel based on what the lateral acceleration and vehicle speed that the simulation itself was like outputting is very difficult to get work. We were able to like have average torque differentials in like different settings and like create a matrix for that and then have like an output. I found that it wasn't making enough of a difference for it to make sense to me. So what we really tried to do was validate it with on-track testing when the car came to be built.
You started with a team of 72 people, ended up with about 54, which is still a pretty sizable team. That's not easy to manage that many people. Tell us a little bit the management software you use, the work breakdown structure setup you had, and so forth. Tell us a little something about that.
Yeah,
A lot of people don't know about that.
So my role in the team was kind of like the design director of the car. John is running up here right now. He's our team captain, and he handled all of the management of the team. So you can give him a round of applause, I guess.
Okay, so as Dave said, managing a team of like anywhere from 70 to 50 people is very much a big challenge. So what we do is we have a pretty good team structure overall. What we do is we have two halves of the team, both the administrative and technical side of the team. Every member on our team has a role on both. So you might be on drivetrain and you're also on PR, for example. And every member has roles that they're assigned each and every week. We use Asana for task tracking, so every week or every given period of time, the lead who is in charge of each member on both sides of the team is able to assign them tasks and give them specific tasks for the week, so they know by whichever amount of time we need to get this, and this done, and it's specific. We also do one-on-ones every single week, so the leads will meet one-on-one with each one of the members every single week, and that allows them to keep track of their progress and catch up with them and see how they're doing. And also importantly, it allows the lead to give feedback on the members and tell them, this week you've been doing a really great job, you've not been doing particularly well, and here's how we can fix that. And that allows every member to grow as an engineer and get that one-on-one coaching that they need to do really well on the team, especially if they're new to the team. That's a big challenge because there's a lot of stuff that happens. And as far as tracking kind of full car progress, that's another big challenge because it's obviously a really large project. There's a lot of moving parts. We use the WBS Schedule Pro software, and that's a critical path structure of schedule. And then what that means is basically we look at if something is getting delayed, it has cascading effects down the line, and every other tech system on the car is linked to that. So I can see if the chassis is going to be delayed by a week, it tells me what's going to happen with aero package, what's going to happen with drivetrain, what's going to happen to the end rollout date of the car. How far is that going to push us back in our first drive? And how is it going to affect us down the line?
I was getting at the importance of managing all your people, because when we talk about design, it's about how you all can interface and get your ideas synthesized and determine who's going to do what. And the project keeps changing as you go. It's not like a manufacturing plant. You're building the same thing over and over. And you that incorporated the software was able to see all those design changes, we call configuration changes in the design. You're able to adapt to it, so you're not doing the work on the old design, which is a bunch of wasted work. So it lets you be a lot more efficient. So bravo to you. Good job with that. It's things a lot of people don't think about when actually designing a vehicle with so many different disciplines. We're going to have to wrap up here because we have three more teams to do. But I want to ask you as well, you picked 10-inch tires, okay? Your car came in at 379 pounds, okay, which is one of the lighter cars, particularly for EV. Tell us about something with your tire selection.
So every C car we built in the past, at least for the last 5 years since we switched from 13-inch wheels to 10-inch wheels, we've been running the 6-inch wide LC0 tires. We found that with our first workable e-car last year, we were actually severely overheating with the excessive power over 50 horsepower YFZ to the two-motor e-car. We were severely, and the extra weight in the weight distribution rearward and the extra mass of the car itself, we were severely overheating our rear tires. So we actually did a small a validation, a physical validation on the cars with our last year's e-car between the 7.5-inch wide R25B and the 6-inch wide R25B. There are merits to both: cornering stiffness, the compound makes about the same total grip, weight, inertia, etc. But what we really wanted to do was minimize weight on this car, make it as simple as possible, make it as efficient as possible. Having the energy constraints we do, we really wanted to minimize the rotating inertia of the car. It ended up we weren't overheating the R25, the 6-inch wide R25Bs. Our tire temperature differential between front and rear was very, very low, about 5 degrees warmer on the front. The LC0s like to get a little bit hotter. And it was definitely an interesting thing. I've had a couple of teams kind of be like, wait, I didn't even know you could do that. But yeah, I think it turned out pretty good, and I'm excited.
I guess the point, you could actually change compounds as part of your analysis
Yeah.
as well. Try different compounds in the front from the rear. You know, some tire engineers say, you can't do that. Well, you do what you need to do to get the car working properly. So always think off the page. You don't just always follow what everyone else says. Think on your own. So, cool. Okay.
Yeah, do you guys have any questions? We didn't come very prepared, so hopefully I have an answer for you.
Who's got
Hi.
the first
I
question?
got a question up here.
What was the management software you guys used?
WBS Schedule Pro. It's the same software that Boeing uses to track their progress on like aircraft building as well. That's where we got it from. We do actually have like WBS design reviews with Boeing engineers at the same time. We have people who like take a look at what we've constructed and see if it's actually valid.
Can you tell me a little bit more about the lap time sim you were talking about? You were talking about sort of comprehensively from acceleration through skid pad, through autocross and endurance. And specifically, I'm curious about sort of what car vehicle models you're using.
Yeah, so it's actually a entirely student designed MATLAB script. It was a master's thesis for a long time, a 7-year student of our team about 6 years ago now. He graduated 6 years ago. But it's been slowly developed more and more in depth. We've developed static events to it. So kind of at a basic level, what we do is so what I did this year was I took Lincoln 2017, the endurance course. Basically what I did was simply take a picture of it, lay it out in SolidWorks, import that SolidWorks into a MATLAB script, and then from that MATLAB script, based on the car's average speed, the car's lap times around that course from the other models, try to compare that to what real times were ran from other competitive cars the previous year. Determine whether or not it's working properly, whether it's accurate to qualitatively, and then go from there, making adjustments and tweaks to not just improve the car, but to try and make it more reasonable. We try to incorporate as many efficiency. That was a large focus for us this year. Drivetrain efficiency, motor efficiency, the motor efficiency maps we get from MRACs. We have Bitchcom models from tires in there. Yeah.
Is it a point mass model, or are you twin track or bicycle? What do you?
For the mass of the car, polar moment of inertia, rolling inertia, things like that. It is a point mass model. I have to actually look at it to confirm an answer with that for you. Sorry about that.
Let's do one last question. Do one last question here. More teams. Either they don't care about your car or they already know and they're espionage.
What does your battery internals look like, specifically cell type and cooling?
Yeah, so we're running, we break our pack down into 5 segments, each of 14 what we call cell groups. Those groups are just 4 pouch cells in parallel. The pouch cells are like a Molasta pouch cell, 6.5 amp hours roughly. Those get bundled together into a group. Their cell tabs get brought over a bus bar, and we just mechanically clamp for the electrical connection. Those bus bars connect between groups to build out the segment, and those bus bars are also a heatsink stock. So we air cool using the actual current path.
Okay, thank you. This is University of Washington.
Thanks, guys. Next electric car, 208, Wisconsin. Come on up, guys.
Jason, Max, what do we got here? Jason Max and his personal photographer. Look at that.
So the Wisconsin car makes use of 10-inch tires as well. They use a 3/4-inch monocoque frame and a 1/4-inch steel subframe in the rear. They use in-hub motors, front and rear, so it's an all-wheel drive car.
And their brakes are on the outside. What's that all about?
And their brakes are on the outside. They do things differently in Wisconsin. I do know they drink a lot of beer in Wisconsin, though, so that's pretty normal. They use front, rear, and side wings. And yeah, instead of skipping all the comments from the design judges, once again, we're bringing it right from the horse's mouth. So guys, take it away. Let's talk about your motors first.
Okay. All right. Hi, I'm Max. I'm the tech director for the team, and here I have Jason, who's the power systems lead. So we'll be talking about the car for a little bit. We designed our own motors this year, which was a huge undertaking. And kind of what drove that decision was really the learning that would happen. Obviously, the performance, when you can control everything, the potential is huge, but we really wanted to learn more about how everything works. And so we took an architecture-driven approach in terms of designing the motors. We also have a lap simulation tool that was written, kind of a lengthy code in MATLAB that's changed over a few years. And we use that to determine exactly what the tire can actually accept. And based on the battery power limit and the tire grip limit, we developed a target torque curve at the tire. And we're able to optimize a compound planetary transmission and the electric motor itself kind of iteratively in order to achieve that tire torque curve in the smallest package possible. And so we had a lot of help from our sponsors to actually make the motors, and we're definitely happy with how they perform. So.
What does each motor weigh?
Each motor is somewhere between 6 and 7 pounds, depending on if you have water in it or not. Water in the water jacket, I should say, not in the motor itself. Yeah, and the pulse performance is 30 kilowatts or 40 horsepower. Continuous performance is much lower than that, but they spin up to 20,000 RPM with 30 newton meters at the shaft, and they're paired with a 14-to-1 compound gear reduction to get all the torque at the tire.
30 newton meters, 14-to-1 gear reduction. Do the math. Let's talk about your battery storage.
Sure. So our battery is based on an 18650 architecture. We used Sony VTC6 cells inside of Energis Power Solutions modules. They make it pretty easy in terms of actually putting the pack together. They come with the fusing and the temperature sensing built in, and we have bus bar connections between them. We actually switched cells from last year from the Samsung 25R to the Sony BTC6 this year, and we did full cell characterization over the full temperature and SOC range for both of the cells, and we're able to generate DC resistance maps. And from that, we were able to show that the Sony BTC6, despite having an extra half amp hour at 3 amp hours per cell, as opposed to the Samsung 25R, it actually had comparable internal resistance, so Sony did a really good job, I guess, making those. And so switching to those, we were able to drop 20% of the battery mass, which is about 30 pounds. It's pretty neat. Yeah.
Tell us about the cooling your accumulator. What material do you use for cooling?
We use the thermal mass.
No water cooling. It's air cooling was sufficient. You proved it.
Yeah, so we did kind of have to choose our battles this year. We're tackling a lot and making our own custom powertrain, and so we did a trade-off analysis and figured that if we power limit during endurance, we can keep the pack energy down with only passive cooling. Water cooling is used everywhere else on the car for both the inverters and the motors, so the system is there, and we're thinking about in future years how maybe we could integrate that into the accumulator itself. But for now, we were able to do the analysis to prove that with a 40 kilowatt power limit, as opposed to the 80 kilowatt imposed rules limit, we can still do well in endurance while maintaining the cells below 60C.
I'm going to ask another managerial type question again, and that is how you manage the members of the team. Mindful of what we just talked about before with software. Was there any software you used? Some subvertive software or subversion software? Tell us more.
Yeah, so managing the team is very difficult. We're a smaller team. Combustion car and electric car are both made by Wisconsin Racing, so we each have about 25 people dedicated to each car. But despite that, there are just as many things to do. And so we have weekly meetings with the leaders with very specific deliverables for that week, and we make sure that we're very organized on a week-to-week basis and that we're getting things done on time that way. We also have Subversion. It's what we use for implementing our CAD software through SolidWorks and keeping everyone up to date at the same time so people can work on designing the car simultaneously without having to worry about someone else editing the model.
For our team communication, we use Slack. Slack's pretty nice because we have channels for each subsystem on the car. So we have a battery channel, inverter channel, general channel, you name it. And that you can also have direct messaging with any team member. So that makes it really easy to get a hold of someone for team communication.
Tell us about. Keep going.
Yeah, so this year we developed a custom quad inverter. This was largely driven off the fact that we defined a set of requirements for the inverter. There's physical packaging requirements, there are the requirements from the motors, requirements from the battery, and we couldn't find any off-the-shelf solutions that met those requirements. So we decided to make our own inverter, and like Max mentioned earlier, we also wanted to learn more about power electronics, so we dove into that world, and it was about a year ago when we first started designing the inverter. We designed schematics over the summer and then worked through PCBs in the fall and actually started testing early in the late fall. And we iterated and tested more on dynamometer and iterated again, and then we got a great working product.
Tell us about, when I was talking to one of your students in finals last night, a comment came up about open source documentation on your car. Tell us about that. I was a little curious.
Yeah, so last year when we first made our first electric car, one of our goals was to do the all-wheel drive architecture and kind of deal with all the challenges that come with that. You see it done in Europe all the time, so there's no reason that can't try to be tackled here in the United States. And so obviously there's a lot of difficulty in getting that actually implemented, and we didn't want to just keep all that learning to ourselves. So if you go to our website, it's wisconsinracing.org, shameless plug. If you go to the electric side, there's a documents section where we have our ESF form. We have a document describing exactly how our lap simulator works from the ground up, design, and also how we kind of put our battery together last year. It's all based on last year's car at the moment, but throughout the summer, after competition's over and we have a little more time, we're going to be writing more documentation and updating those on our website. So we want to make sure that everybody can learn with us.
I'll make sure I heard that right. They're giving their design away largely. Okay.
Yeah.
So. We'll take advantage of that. Questions from the field for these students? University of Wisconsin.
Man, this is a quiet audience.
Here we go.
Hey there. For your Energis packs, what temperature circuit did you build to monitor all of your Energis batteries?
So inside the Energis module is a temperature-dependent Zener diode. So basically, you just have a voltage divider circuit with the Zener diode, and then we have that signal feeding into one of our BMS chips, which is the LTC6811 from Linear Technologies. And yeah, then we send that information from the battery slave board to our battery master board, and then it decides what to do with that.
Others?
Anyone else?
Got to be some more questions for them.
Can I do one?
Yes, James, you may ask a question after this.
So I guess in terms of design and optimization for designing your own stuff, how did you guys decide that it was worth the effort to design your own inverter and motors, but not your own battery modules?
It's a good question. I would say that our goals based on the interests of the team members themselves were more oriented towards the the inverter and motor side of the powertrain, and it really just boiled down to who we have and how much they're willing to, put all of that time in to figure those things out. We're also happy actually with how the Energis modules worked last year. They're like very simple to put together, and like I said, they take care of all of the fusing and temperature sensing for us. So we were happy with that as it was, and it's definitely something that the team is going to look into in the future, but can only do so much in 1 year. So yeah, plans for the future definitely.
I can add to that. So the Energis modules are great. They met all our requirements, so we saw no need to make our own modules. Whereas with the inverter, there wasn't really anything out there that we were happy with. And in terms of the motors, we could get significant performance gains by making our own. So that's one of the main reasons was that there wasn't much, we didn't see much benefit for making our own modules.
A little tough to go find an integrated brake and motor together on that, right? To fit your parameters. Come take a look at later on when you see the car. You'll see what they do with the front brakes. It's quite interesting for the packaging for the front drive motors. James, you got a question? Better question from a student. All right.
Yeah, I was just curious of your motor architecture. Is it permanent magnet AC, permanent magnet DC? And why did you choose such a high RPM motor?
Yeah, that's a great question. So these motors are permanent magnet motors. They're interior permanent magnet motors, and the lamination geometry for the stator and the rotor is completely custom. And we, like I said, we worked with a lot of sponsors to actually make them. The reason why we went with a permanent magnet design and an interior permanent magnet design in particular was because of the power density that you can get out of it. And also, in particular, with the IPM style motors, you can get a nice wide constant power band in the flux weakening region of the motor by burying the magnets in the rotor steel. So that kind of goes to that side. But in terms of the speed, that's a good question. The most significant load case for the motor itself was the rotor burst case in speed. At 20,000 RPM, it's like 13,000 Gs or something at the tangential to the rotor. So that was a very difficult challenge. But power density comes from two places. It's torque density and speed. And so speed's kind of the easy one. You make it spin as fast as you can. Torque density just comes from the selection of the materials. So we use the best materials possible everywhere. And so the combination of those things results in a motor that's 10 kilowatts per kilogram.
We got to keep going.
All right, thank you.
One last question here.
Because you used multiple motors, how did you guys deal with torque vectoring for like those 4 motors?
So torque vectoring, and this is kind of similar to what the Washington guys said, there's like so many ways you can do it. We have 2 ways in particular. There's a simple way, and then there's a more complex way that we can use based on data that we gather. The simple way is using a bicycle model. So for a given steering angle and vehicle speed and wheelbase, you can figure out what yaw rate the car will steady out at for if you hold the steering wheel at that angle. So just a simple bicycle model in that sense. So when the car is actually moving, the ECU is looking at what that predicted steady state speed would be, or steady state yaw rate would be, compares it to the current yaw rate, and then has a yaw moment that's added to the vehicle by powering down and powering up different sides of the car to actually achieve that. And then the second more complex way is if you do a bunch of steady state circles, you can actually get the data for your steady state yaw rate versus steering angle. And that actually captures your roll stiffness distribution. And so if you can do a bunch of steady state circles, you can actually plug that into a lookup table in the ECU. So the ECU actually knows where the car is going to get. And then at that point, you can crank the gains up. And that's where it starts to get really interesting.
So I have a question too. Do you have a limp home mode if you lose 1, 2, or 3 motors?
Yeah, we do. So we have our fault manager that we use in MotoTune, where we can calibrate the car on the fly. And the way we set it up is if there is a soft fault, so software catches a fault in one of the inverters, we can turn off just one axle. So if there's a front motor fault, we'll turn it off. If there's a rear axle fault, we'll turn it off. If there's a hard fault, a hardware-driven fault, we usually just kick the car out of high voltage just to make sure everything's safe. But we definitely like to have the contingency mode wherever possible. Yeah.
Okay, car number 208, University of Wisconsin-Madison. Thank you.
Okay, so I'm going to shift over to the more traditionally powered cars, internal combustion cars. We'll start with the one closest to us here, which is car number 79. Auburn, War Eagles, want to come on up, two of you? Nick or Evan, maybe Payson, maybe three of you.
Auburn elected to build a 10-inch tired car, monocoque chassis. They use a four-cylinder engine. It had a 6-speed transmission. They take 2 gears out. It's run with 4 speeds only. They run a spool differential, correct? No differential. It's a spool. Their statement to me when I asked them why you're running carbon fiber instead of the traditional school colors was, testing time beats painting time. And I happen to agree with that statement. I like it a lot. So without further ado, let's hear from them about their car. Talk about the engine first?
Yeah. So we actually switched back to a 4-cylinder this year. Some of you know we switched to a 2-cylinder last year. Switched to a full monocoque. Had issues with like being able to maintain the car, and after doing more analysis, determined that the extra weight of the 4-cylinder would benefit us more because after doing torsional stiffness testing of both engines, we determined that weight, the added weight of the engine, could then be saved in the chassis by stressing the engine. So that was one big thing. Part of the selection of going with the 4-cylinder is that we're all amateur drivers on our team. We're not professionals, and just a momentum car is a lot harder to drive. Being fast in a car that doesn't have a lot of power is a lot harder than being fast in a car that has a lot of power. So just making a car that's fast and reliable and can be driven up to its potential was like paramount to us.
Tell us about your dyno program and your on-track dyno program, if you will. I think I use the car as the dyno. Actually, for your brake dyno, I guess it was.
We don't have a.
Oh wait.
So we have an engine dyno that we do. We have an engine dyno that we do engine testing on for a large portion of the early part of our design season to do physical validation for engine stuff. And we get to do a lot of tuning off the car and solving issues before the chassis is even ready to accept the engine. So then once the chassis starts coming together, we can just throw the engine in and start getting testing time. And we try to run a really similar setup on our engine dyno to what we run in the car. So we'll set up the fuel system the same for the most part. And we have a really nice engine dyno that was done by a grad student for us that is can be really easily accommodated with new sensors, new ways to collect data on the engines. So one of the things that was accommodated for was cylinder pressure testing. We haven't got to start doing that testing yet, but we have all of the things we need to do it. And so that's one of the things that we're going to expand on in coming years to try to help get better efficiency and just get more performance out of our engines. And then once we're done building the car, we'll put it on the chassis dyno, and we do a lot more tuning on the engine. We do a lot with ETC to make the car extremely drivable. We choose a really large ETC because we have the ability to change how the position of the pedal relates to the position of ETC. So we'll do a lot of sweeps through different percentages of throttle position and figure out where the pedal is the most sensitive, and basically adjust the pedal so that the driver gets the most resolution in the areas where the car is most driven at steady state.
Okay, you've got titanium wheel studs, and there's only 3 per hub. Tech was pretty concerned about it, but I know you did some pretty extensive testing on it. Tell us a little bit about that.
All right, so that was part of my job this year. I did, one of the things that I did on the car this year was hubs, uprights, and wheels, wheel centers. We, in the past, have used 4 lugs, the same exact titanium lug studs. And to start off, some of the analysis that I did on the lug studs included the force in the lug studs due to longitudinal acceleration and lateral acceleration. So the forces in the studs due to overturning moment, the forces in the studs due to rotational torque at the wheels. And basically, if you're using your studs correctly, the studs are never put in shear. You're using the friction between the wheel center and the hub to carry that torsional load. And also, the second part of that is when they're put in an overturning moment in a hard corner, you want to make sure that you're not cycling them. So you want to make sure that the tension that is put on the stud by the nut is greater than the force that it's going to see in a hard corner. So if that is not the case, every time the wheel rotates and the stud goes in tension on the top side and you put the hub in compression on the bottom side, you're cycling that stud. So if it can see 20 cycles of you tightening it down to torque spec, but it's being cycled every time the wheel rotates, it's going to fail immediately. So doing that, I assumed a worst case scenario. I used frictional values of aluminum on aluminum for greasy surfaces, and selected my torque spec for the studs based on those friction values and what was necessary to react those forces in that case.
Well thought out solution and engineered with the knowledge to back it up. They brought the engineering data with them to design judging. They backed up their design with validated and tested efforts. It's a good effort. Car weighs 396 pounds. It's no slouch. It's a pretty lightweight car. Some of the comments from the design judges: excellent cockpit and steering wheel design. The ergo judges really enjoyed sitting in this car. It was comfortable. You can get right down to business in this car and make it drive. Here's a note from Claude that he passed along. Impressive vehicle dynamic knowledge in theory and practice, able to answer all questions pretty well, from Claude Ruel. Thank you very much. Dave?
Yeah, use the dampers quite a bit to get the tire temperatures proper. A lot of testing you've done there. What was good is you actually use data to back it up, rather than just, oh, it feels good using the driver. You use the data to back up, all of your analyses. Your dynamics you got right in transition, the roll and transient steering and yaw you got figured out pretty nicely too. Basically, what it was a nice holistic view. The whole car was just done right throughout. I mean, it's one of those cars you just like to hop in and drive right now. What I did notice is that your team leader is not an engineer. That might be a surprise, okay? And actually, I think it was a brilliant idea because they took a very, very great high-level view of the vehicle, not just the vehicle, the whole team, okay? And we engineers have a little trouble communicating at times with each other in the right way, and he's got the right approach. So I think you should consider that because he also knows the types of people you'll need, whether marketing people, or the finance people, or the maybe even some people doing human factors engineering and stuff like that, and the medical schools and so forth. The idea is look at those other disciplines, and so that was a very interesting to see. So keep that in mind when you're looking at your teams in the future. MATLAB algorithm for your all analysis to tune the chassis was quite good. There was a couple comments. The pedals, well, you have really great adjustments of the pedals, but the heel cups were not as secure as they would have liked. So with every single silver lining to that cloud, there is still a cloud. And I want to ask you one question. What happened to you in endurance today?
Well, hang on. Let me just get to one point first. I'm sure that all of you watched yesterday's performance, and I have to give a little bit of an attaboy to this team for yesterday's performance. This is almost fairy tale stuff. They won skid pad, acceleration, and autocross all in one event. And we're looking into this right now. I still haven't gotten a solid answer from the official Formula SAE scorekeeper, but we think you're maybe the only car that's done this so far. And I'll give my attaboy to Auburn right now. Thank you very much. Congratulations. You guys put on a hell of a show yesterday. I know their faculty advisor pretty darn well. I've been down to their school a couple of times on SAE lectures, and I can tell you that yesterday he was talking and walking about 3 feet off the ground all day long. It was like a fairy tale deal. Now, Dave, it's time for Dave to talk about something else that happened today.
Okay, so we want to see it was a clean sweep of dynamic events. So a lot of us judges were out there with great anticipation, hanging out on the golf carts, walking by the course, and seemed to have a lot of intermittent engine behavior out there. Tell us what happened.
So basically, it was a really stupid issue. So we have a vacuum tube that goes into the top of the fuel tank, and oh, it wasn't.
So basically what happened was we have a vent. So you have to have your fuel vent to ventilate the fuel system. The same one that's tested in rollover, or in tilt. And the vent line was zip tied too tight to the space frame, sealing the vent tube. And throughout endurance, as the fuel was leaving the tank, we were pulling a vacuum on the fuel system. And the further and further we got into endurance, the worse and worse it got. And about, say like 2/3 of the way through, it got to the point where the fuel pump was pulling so much current that we were hitting an overcurrent limit. And the PDM, which is our power distribution module, we set current limits for each system on the car based on known values that those systems should not exceed. Our fuel pump was set at 10 amps, and once the fuel system got a sufficient vacuum pulled on it for the fuel pump to exceed that amperage setting, it began to kill the fuel pump to try to save that system. And basically, I was driving the car at the time, and I was having to drive the car with one wheel and cycle the fuel switch with the other hand about every 2 seconds to keep the car going. And eventually it just got to the point where I couldn't cycle it fast enough, and the ECU couldn't reset, or the PDM couldn't reset the state of the fuel pump fast enough to just keep the car going. Because initially we thought we just had a fuel issue where the fuel pump wasn't deep enough down in the tank and we were just not picking up fuel. But it's got a 2-gallon tank, and we showed up to fuel and put like a gallon and a quarter of fuel in it. So just a really unfortunate situation. It just happens in racing, so.
So if we understand this, all the sophistication, all the work that's done, this let you down. Okay. Something to remember, the smallest thing can get you. If any consolation, this almost exact thing happened to one of my guys a couple weeks ago at the June Sprints. It's resetting the PDM because the sensor was drawing too much current, and the ECU happened to be on the fuel pump. Worse than that was the keypad, which kept making the whole thing go, the whole PDM go. So you got to pay attention to details. When we talk about holistic engineering and all that stuff, you still got to get the details right. So it's a lesson learned, but still fantastic work.
Still one hell of a performance from Auburn. Thank you very much. Car number 75, 79, Auburn University. Thanks, guys. Great performance. Great performance.
Okay, Spartans. Paul, Ajit, who have we got here?
Michigan State rolls on 10-inch tires. They do a 3/4-inch monocoque and a 1/4-inch rear subframe car. CBR 600 4-cylinder. They run 93 octane fuel. They're naturally aspirated. They run a Drexler differential. They also run a 4-speed gearbox. They eliminate 2 of the speeds out of their 6-speed transmission. They run a 3-element rear wing and an underwing, and a 2 and 3-element front wing and a rear diffuser. So let's get right down to it. Tell us about your engine strategy. You guys have always made power. Tell us about it.
All right, so to start with our engine, we initially start designing it using Ricardo Wave, and we use that to design our intake and exhaust, plenum volumes, runner lengths, that kind of thing. And then with the intake, we verify that using CFD, Star CCM. And so we basically use that to dictate the geometry of our intake to make sure everything's flowing correctly. We're getting equal distribution to all 4 cylinders. And then we've also used that to design our diffuser, which we use to basically just try and get as much air as possible through that tiny restrictor that we can. So then from there, we also use Ricardo. Initially, when we started using this, the RR, we used Ricardo to get our spark advance and our fueling, and we used that as a starting point for our dyno data. So then we were able to use an in-house engine dynamometer to actually create max torque at our, I guess, desired fuel calibration and spark calibration.
Okay, I want to talk about your team a little bit here, if we can. Go ahead. You got a mentoring program for newbies to come in. Tell us a little bit how you indoctrinate the newer, I shouldn't say hazing, but how you bring in the new students and make them be a member of the team the way they should be. Tell us about that.
So initially we have basically throughout the engineering college, and then we also recruit to the business college, and basically it's just initial meetings to get them interested in the team, explain what the team is. From there we'll have them out to the shop, and they'll kind of get to see the cars, see what we do. From there, we go into training them on all the machines. Some of them get welding training, things like that. And then from there, they kind of divide into systems. And as soon as they kind of get hooked onto a system or systems, they'll get assigned new member projects. Some things such as like tire temp mounts, things like that. They can kind of get involved and really start actually designing and manufacturing even for the current car.
It's not quite what I was told. I was told you give them some really tough work to do, and if they can do it right, they stick around. Not in a mean way, but really, tolerancing, make sure it's done right, and they've got the right attitude, and then they'll stick with you for the whole rest of the time there. Is that?
Yep, so that's one of the big things we kind of focus on when looking at new members is a lot of people are really intimidated that they don't have the vehicle knowledge that you need to start with something like this. And we have the resources and the older members to actually teach people. So what we're really looking for is dedication, because as I'm sure all of you know, actually building and competing with one of these cars, you have to do some pretty crazy things, pull all-nighters and everything. And if you have members that aren't willing to do that right at the beginning, then they're not going to be willing to do it right when you're leading up to competition. So that's one of the big things that we focus on is trying to get new members coming out to the shop 3-4 times a week, and then just grinding on machines, mills, and lathes to start out. And then, so we recruit around October, and then starting in mid-December during our winter break, that's when we start opening them up more into, all right, let's teach them a little bit more about the systems that they're interested in, and kind of get them more knowledgeable about the car itself.
So you're running a Drexler rear end. Obviously, there's a bit of tuning that goes into it. How do you decide how to tune your Drexler? Are you guys versed on tuning Drexlers? Or have I got the wrong 2 guys up here?
What we mainly use our Drexler as kind of a driver feedback type system so far. So initially last year, what we've done is we were having a lot of complaints on low speed understeer. So we opened up the differential, and then we made a lot of changes with track width and wheelbase this year. So it changed a lot of the handling of the car. But we started out with that initial open differential. So then later throughout the year, we figured out we were actually having trouble unloading our right rear tire slightly, and that would cause our wheel to spin. And so because how open the diff was, we weren't actually getting any power to that outside wheel. And so we tuned it to actually lock more under acceleration, and that actually helped a lot also because our autocross and endurance drivers started out as karting drivers, so they really liked the more locking diff as well.
Yeah, let's take some questions from the audience.
What was your team major goals, and how did you come to them?
So every year we sit down pretty much right after the Michigan competition, and we elect our new system and project leads, and then we'll have our initial design meeting. And during this meeting, we set overall vehicle and team goals. This past year, it was a redesign year, so about every 3 years we redesign the monocoque, so it gives us complete design freedom. So we had the design goals of early completion date, weight reduction, and system integration because of the redesign.
Hi. You said you did CFD work on the intake. What was your setup for that? How in depth did you go?
I am not the person to ask. We got
Another question?
Yeah. Sorry, I don't have a whole lot on that for you. I really didn't do any of the CFD work myself.
All right, fair enough.
Hello. All right, so pretty much for our CFD, for our intake model, we use a K-epsilon turbulence model, and we just use steady state CFD, no transient. And pretty much what we're looking for is really smooth flow throughout the elbow and then all the way to the runners. We don't really tune like the plenum volume or anything like that with CFD. We pretty much just look for the smoothest flow possible and the most mass flow to all of the cylinders. And yeah, that's pretty much it. And then we also, sorry, one more thing. We also design a restrictor around it, and we use flow bench data to make sure that our CFD model is actually accurate.
Time for one more question here.
What's the correlation between the flow bench and the CFD? Yeah, like percent?
So one of the biggest things that we look at is just through the restrictor. So the percent difference between the flow bench and the CFD for just the restrictor portion was about 0.9%.
All right, Michigan State University, thank you very, very much.